Vanakkam makkale, in other words, welcome back to a brand new episode. As you guys may or may not have caught on from the last episode, I decided to shake things up a bit. Not only do I have a new name for my podcast this time around, I also thought I should lighten things up. Things felt a little too boring. So புதுசா ஆரம்பிக்கலாம், a fresh start. Now ungal Shruti, and let's get into this week's episode on, drumroll please, Konjam Mokka with science. Now, like I promised last week, let's look at a bit of geometry, i.e. shapes in nature. Patterns in geometry seem to be everywhere in nature. For example, the earth is a sphere. Okay, I know we all know that. How about spider webs, or an obvious one, a starfish? I think we get the idea. There are shapes in nature. But have you ever noticed that nature seems to have something particular for the number 6? Beehives, rocks, marine skeletons, insect eyes? Are these just coincidences, or could there be some pattern beneath the pattern as to why nature arrives at this geometry? Well, this can be explained using everyone's favorite, bubbles. What are bubbles though? Come on, Shruti, don't you know what bubbles are? No, of course I know what bubbles are. Fun-filled spheres that burn when they pop close to your eyes. But I meant scientifically. A bubble is just some volume of gas surrounded by liquid. It can be surrounded by a lot of liquid, like in champagne, I wish I knew what that tasted like, or just a thin layer, like in soap bubbles. While blowing bubbles, have you ever wondered why these bubbles have any shape at all? You may think, yes, Shruti, I was 6 years old blowing bubbles to my heart's content and was thinking of the math behind bubbles. I get where you're coming from, but just wonder with me, for my sake at least. Liquid molecules are happier wrapped up in the middle, where attraction is balanced, than they are at the edge. Hey, apparently even water molecules like being the center of attention. This pushed liquids to adopt shapes with the least surface. In zero gravity, this attraction pulls water into round blobs. Same with droplets on leaves or a spider's web. Inside thin soap films, attraction between soap molecules shrinks the bubble until the pull of surface tension is balanced by the air pressure pushing out. I know I promised math, but I've got to be honest. This is because of physics. But physics does involve a lot of math, so I guess it wasn't all lies. Let's look at the physics of bubbles, which does include math. Bubbles are round because if you want to enclose the maximum volume with the least surface area, a sphere is the most efficient shape. I guess that's just putting what I already said in a different way, but never mind that. What is cool is that if we try to deform that bubble, the pull of surface tension always evens back out to the minimal surface shape. That explains my repeated childhood failure at heart-shaped bubbles. I just always thought bubbles were too stubborn or something. Now you guys may ask me, what does all this talk about bubbles and spheres have to do with hexagons? Be patient, we're getting there. Now what happens when we start to pack these bubbles together? A sphere is a three-dimensional shape, but when we pack bubbles in a single layer, we really only have to look at the cross-section, a circle. Rigid circles of equal diameter can cover at most 90% of the area on a plane, but luckily, bubbles aren't rigid. Let's pretend for a moment these bubbles were free to choose any shape they wanted. If we were to tile a plane with cells of equal size and no wasted area, we only really have 3 regular polygons to choose from: triangles, squares, or hexagons. So which is best? Now picture this with me. You can use real bubbles if you have them. You're blowing 2 equal-sized bubbles close to each other so they touch on a glass panel. You see a flat intersection. 3 bubbles and we get walls meeting at 120 degrees. But when we add a 4th, instead of a square intersection, the bubbles always rearrange themselves so their intersections are always 120 degrees, the same angle that defines a hexagon. I really bet you paid attention in math now. If the goal is to minimize the perimeter for a given area, it turns out that hexagonal way of packing beats triangles and squares. In other words, hexagons offer more filling with fewer edges. Now for some facts. In the late 19th century, Belgian physicist Joseph Plateau calculated that junctions of 120 degrees are also the most mechanically stable arrangement, while also allowing the forces on the films to all be in balance. That's why, when we gently squish bubbles together on a flat surface, they form hexagonal patterns. Not only does it minimize the perimeter, but the pull of surface tension in each direction is the most mechanically stable. For those still confused minds, let's review. The air inside a bubble wants to fill the most area possible, but there's a force, surface tension, that wants to minimize the perimeter. And when the bubbles join up, the best balance of fewer edges and mechanical stability is, you guessed it, hexagonal packing. But is this enough to explain some of the six-sided patterns we see in nature? Basalt columns, essentially just hexagonal columns like Giant's Causeway, Devil's Postpal, or the newly found basalt columns in Kolhapur, Maharashtra, form from slowly cooling lava. Cooling pulls the rock to fill less space, just like surface tension pulls on soap film. Cracks form to release tension, to reach mechanical stability, and more energy is released per crack if they meet at 120 degrees. Sounds pretty close to bubbles, doesn't it? The forces are different, but it's like using similar math to solve a similar problem. Well, what about the facets of an insect's eye? Here, instead of a physical force, like in bubbles or the rocks, evolution is the driver. Maximum light sensing area, that's good for the insect, but so is minimizing the amount of cell material around the edges. Once again, just like the bubbles, the best shapes are hexagons. What's even cooler is if you look down at the bottom of each facet, there's a cluster of 4 cone cells, packed just like bubbles. Well, I just talked about all sorts of strange places in nature where we can find hexagons. What about the most obvious one? Honeycombs. Although it would be nice to imagine little number-crunching mathematician bees experimenting with triangles and squares and realizing hexagons are the most efficient balance of wax to area, but with a brain the size of a poppy seed, they're no mathematicians, are they? It actually turns out honeybees make round wax cells at first, and as the wax is softened by heat from busy little bees, it's pulled by surface tension into stable hexagonal shapes, once again, just like our bubbles. So, is nature a mathematician or not? Some might say nature loves efficiency, or maybe that nature seeks out the lowest energy. Next time your mom complains of your laziness, you know now to say, it's in my nature. Take that, Mom. Others might say nature is just following the rules of mathematics. However you look at it, nature definitely has a way of using simple rules to create elegant solutions. Hope you guys enjoyed my changes, but I have a question for you guys. Am I that flawless that you guys don't have any comments for me? Well, until next week, Nandri Vanakkam, stay safe and stay curious.